Hello and welcome back to another video. In this problem, we're asked to locate the discontinuities of the function and illustrate by graphing. So we have y is equal to ln of tangent squared of x, and we can see that this is a logarithm taking on a trig function. And we know from theorem 7 that log and trig functions are continuous over their domains. And we know from theorem 9 that if a function is, if a composition, right, so log of a trig, not like log plus trig, if we have a composition of two functions where we have like one function taking on another function, and we have the, let's say, at a value a, right? The trig function tangent squared of x, if this is continuous at a, and ln is continuous not at a, but at tangent squared of a, then the whole function is continuous. So we can restrict this function to have discontinuities only at points that are outside of its domain. So at what values is this function, does it not exist? Well, the natural log function, if we have ln of y, this exists for y is greater than 0. Therefore, tangent squared of x here has to be greater than 0. However, tangent squared of x is always positive or equal to 0. So the only thing this is restricting is when tangent squared of x is equal to 0. That is caught in. However, we also have to consider where tangent is restricted. And if we know the graph of the tangent function, right, it looks like this. If I could draw it better, where it's like cyclical and we have restrictions at points that are pi away from pi over 2, right? So it could be, k could be 1, 2, 3, 4, 5, however many pi away, and also in the negative direction. But at these values, right, the function doesn't exist. And therefore, we have to take the fact that these restrictions are the restrictions at which this whole function is discontinuous, because those are the only values where it does not exist. Therefore, where k belongs to the integers, which we denote by z, these are the discontinuities of the function, which we can see if we've graphed it as so. Have it pulled up right here. We can see we have these cyclical discontinuities.